All right, I'm ready to start if you guys are. Yes? Yes. Okay. The very first thing, they can try to move me over to botany and get me out of Belter and try to put me in a fragrance-restricted zone, but they won't shut me up. I promise you that. No. Rule number 1, please do shower, use soap, use fragrances, deodorant. We're all going to suffer here if we really take that fragrance. I don't know if you know what I'm talking about. Never seen this in my life, but posted right on the doors all over this building are fragrance-free zones. Please don't wear cologne, aftershave, deodorant. Okay, you have my permission. I'll take the heat. Okay, my name is Dirk Bondy. My first name is Kenneth. My father's first name is Kenneth, and we'll talk about him in a minute. I go by my middle name. I'm a structural engineer in the state of California, Nevada, Hawaii, Arizona. That's about all I want to tell you about myself right now, though. I'll tell you over the course of time more things about myself, but I'm in the mood more to talk about the things I think about instead of what I've done or who I am. I'll start with this material. Prestressed concrete is the most fascinating, interesting design material that there is. You can write that down. That's not my opinion, that's a fact. It's pretty close to a fact. For that reason, you're going to see things in a way you've never seen them before. You're going to think about materials and design in a way you've never thought about it before. This is just a very different, strange, unique, and wonderful material. Because of that, a lot of people are afraid of it. A lot of design people are afraid of it, and a lot of academic people are afraid of it. We are going to put some very large forces into buildings. That's what pre-stressing concrete is. I'll get into the nitty-gritty in a minute, but we're going to squeeze concrete. Lots of force in it. Engineers by nature and everything you've done has been a very passive thing. You've been given loads, you've been told you need to support this, you need to hold this up. Earthquakes, vertical loads, lateral loads. I doubt you have ever put the force into a building, and very large forces. But we're going to actively put forces into the building, and we're not going to be passive. We're active, we're aggressive. It's a whole different concept. And again, those things scare people. And I'm sorry if I'm sweating. I've been walking all over campus and trying to find the best way to get here, and all I did was work myself up. But, pre-stressed concrete is taught in very few schools, and fewer all the time. In fact, UCLA was one of the schools that was canceling this class. My alma mater, Cal Poly San Luis Obispo, did cancel the class. Very few schools across the country and across the world even teach it. So you may be asking yourself, why, if I just told you it's the most fascinating, interesting, wonderful material that there is, why are so few people, schools, academics, teaching it? And so few students interested in taking it? That'd be a great question if that was your question. I guess I have a few answers. I've got some ideas. First of all, to teach this correctly, you have to attack it. You have to understand that concrete, cast-in-place concrete, is never a simply supported material. The beauty of fluid cast-in-place concrete is its indeterminate nature. The fact that it can be multi-spans, the fact that you'll have negative and positive moments. I took this class at Cal Poly in San Luis Obispo in the 80s. In the late 80s, I took it again in Berkeley as a graduate student. I had undergraduate at Cal Poly and graduate there at Berkeley. So I had 10 weeks of it at Cal Poly and 15 weeks of it at Berkeley. And I will be honest with you, I learned almost nothing useful. And I don't mean to be mean. I had great professors. They gave it their best shot. They were not practicing engineers. And I think this is one of those materials that really needs to be taught by somebody who practices it. And by the way, I've practiced it since 1989. So the teachers are teaching it using simply supported methods, not showing you the great and really wonderful things that can happen. that you can only see in this material if you look at multi-spans, indeterminate systems. So we're going to dive into indeterminate systems as fast as we can. Within the second week, I'm going to give you a method to analyze multi-span beams, and we're going to spend the rest of the course after that looking at how great this really can be. But without a few tools, it's going to be difficult. It's funny, I've been contacted by a professor from a school back east, and they said, well, we see what you've done, and I've actually offered up my notes to people. I've got a book out. I've tried to get this material to be taught well. And they tell me, well, it's interesting that you do two-dimensional multi-span systems, but the world's gone to three-dimensional finite element systems. So our schools are just bypassing that altogether. We go straight, we either teach it simply supported or we teach computers and finite element methods. And to me, that is absolutely ridiculous to expect that anybody's going to ever understand, going from crawling to sprinting without ever walking. And I've got opinions on finite elements and programs like that. I took finite elements from Ed Wilson at Berkeley. He was one of the developers of it, and he's also its biggest critic, interestingly enough. Professor Wallace and I were actually at Berkeley within a year of each other, too, so I think we took a lot of the same courses. But another thing that's kind of a pet peeve of mine is they call this a design course, but when I took it, I didn't learn anything about design. In fact, that's kind of true with most of the materials that I took. They kind of shoot at you, we're going to do shear, and then we're going to look at bolts, and then we're going to look at flexion, and then we're going to look at deflection, and you kind of get this hodgepodge of things thrown at you without really understanding when you go out and get your first job and sit down at your desk what you're going to get, what you're going to be given, what you're going to have to figure out, what the first step is, what the second step is. So this class will be a design class. I will show you, I'll kind of do what everybody else does. I'm going to spit things at you in homework assignments. We'll have 6 of those. They will be basically in the chronological order of the way you're going to design it, but then we are going to loop back around with a project, and in that project I'm going to give you exactly what you would get out at your first design job. And I will show you what needs to be done first, what needs to be done second, and you will do a true design following, basically the way you will do it at your office. And you will think in terms of design, and you will graduate understanding, actually feeling like you took a design class, I think. Now, again, whose fault is it that this isn't a real popular course? I've blamed the academics, and it's popular to blame the academic crowd. But I don't really blame them as much anymore, especially since I got back into the academic world. This is a tough material to teach. Especially if you haven't designed it and spent a large chunk of your life thinking about it. But I also think ACI, the American Concrete Institute, one that we all love and live by, holds some blame for this. And every year that I teach this class, I feel that way more and more. For the most part, we're going to have 9 weeks of academic bliss. You're just going to love it, I promise. And I'm not going to sweat so much because I'm going to drink a lot of water before I get here. But we're going to take 1 week and have to do what you did in reinforced concrete. We're going to have to design for shear. Once the code gets involved, most of everything we're going to do is statics, and it's going to be elastic properties, and it's going to be physics, and it's going to be strength of materials, the things you've learned, and the things that no code can ever really change. But once the codes get involved, sometimes they can really mess it up. And ACI is very guilty in this particular case. Their shear design is the most difficult, most complicated, and biggest turnoff that there is. And it almost depresses me. We're 7 weeks away from that, but there are going to be a lot of people watching me sweat in the very first lecture here. They're going to tune in and probably only watch the first half hour. you know, I'll tell you about that in a minute, but the lectures that I have given last year have actually been watched throughout the world. It's pretty interesting. It's pretty fascinating. So I want to get my grievances about ACI and shear out, so they know how I feel. Very complex shear equations. So a teacher who's got to teach this has got to face that eventually, and it's miserable, and it really is. And most classes, when I took it, I think 2 out of our 10 weeks at Cal Poly were based on shear, beam shear, and probably 3 weeks up at Berkeley, and it just sours you on this. And it sours the students, it sours, you know, the instructor doesn't really want to teach it, it doesn't make any sense. So my approach in this is to, you know, we're only going to spend 1 week on it, but we're going to dive into it, and I'm going to teach you to hate it, just like I do. I'm going to give you a miserable homework assignment. You're going to work very hard at it. You're going to get results that don't make any sense to any common sense person, any engineer with any background at all. And you'll leave this class hopefully disliking it as much as I do. And my hope is that if I can get to enough people, you know, maybe one of you will get involved in ACI someday and make a change, and it'll be you. I've tried and they ignore me. I'll talk a little bit more about that in a minute. But let's look at other materials. What is the shear capacity in steel? Isn't it 0.6 Fy times the web area? I mean, they make it about that simple. When I learned it, we used allowable stress design, something that's totally foreign to you, but I will talk about that in a minute too. It was 0.4 Fy, but that was an allowable stress. That was not a load-resistant factor design stress. In reinforced concrete, in reinforced concrete, we had the nominal shear capacity was equal to the concrete portion plus the steel portion. We're going to have that. This is the same exact thing in prestressed concrete, and we put fees in front of it. What was this in reinforced concrete? I know you remember. 2 square root F prime C. Reinforced concrete said that's all you need to know. That's all you need to do. That's the equation to get to VC. Again, in steel, 0.6 Fy times the web area. Now, sometimes in steel, you're always trying to make sure it doesn't buckle. The flange doesn't want you don't want the flange to buckle. You don't want the web to buckle. So, you know, they teach you in school to do all kinds of high-tech equations, see if it's going to buckle. And in practice, we just weld on stiffener plates all the time. That's the quick and dirty. Don't tell anybody I said that, but if I were even thinking that it might buckle, we just weld on stiffeners. But I did a lot of steel, by the way. I actually worked for Tom Sable at Engelkirk's office for 7 years. Did more steel than I did concrete. It wasn't till I left. I did some pre-stressed concrete. Engelkirk was a great place. We learned all kinds of things. I did some wood. I did a lot of steel, concrete, pre-stressed concrete. But I'm no stranger to steel. And by the way, in wood, I did some wood there too. Shear in wood, you just look it up. If it's Douglas, I know wood's not taught here, and that's okay. But you just look up the shear capacity of wood. If it's Douglas fir number 1, you just look up F sub V in a table. If it's select structural or grandma's birch tree in her backyard, there's a value for it. You look it up. That's what it is. You multiply it by the shear area, the web area, and you're done. Now, I don't want you to run for the door, but in pre-stressed concrete, and by the way, 2 square root F prime C, where in the span is that? Trick question. Anywhere in the span. That was always the case. 2 square root F prime C. Didn't matter if it was by the support, negative bending, positive bending, anyway, it was 2 square root F prime C times BWD. But anywhere in there. And in the steel beam, it's 0.6 Fy times the web area, anywhere, one end or the other. Same in wood. Well, guess what, a pre-stressed concrete? Not so much. At every single location, you know, you're 3 feet from the support, and we're going to do this. You're going to hate it. You need to know what the shear capacity of the concrete, just the shear capacity of the concrete only. And by the way, in pre-stressed concrete, you're going to learn that we're squeezing that concrete and we're lifting it. So the concrete itself is almost flat. It's really not bending much. That's the beauty of pre-stressed concrete. You'll see that shortly. But the whole reason we do it is concrete wants to sag, we pre-stress it and lift it back up. We squeeze it. Concrete wants to crack, we squeeze it so it doesn't. So the concrete in pre-stressed concrete is effectively flat and in compression, just what concrete wants to be. So you'd think that would make it even easier. I would. But it's not. It's very difficult. You need to know the factored moment at a single location in order to calculate what the shear capacity of the concrete is. You need to know the depth to the pre-stressing steel in order to figure out what VC is in pre-stressed concrete. You need to know what the dead load only shear at that particular location is. The dead load shear, in order to know what VC, what the capacity of the concrete and shear is. You need to know an equation called V sub I, which is the shear, but only due to loads after the member has been pre-stressed. So the dead weight of the member is part of the pre-stressing load. It's part of the load that's there before it's pre-stressed. So we're just looking at loads after dead load. You need to know that. You need to know in order to just calculate VC. You think I'm kidding. I'm not kidding. We actually have to do all of that. We have to know what the moment is at that one location due to loads applied after the pre-stressing happened. We need to know the moment with loads applied after the pre-stressing to figure out just what VC is. Remember, all it was 2 square root F prime C, done in reinforced concrete. We're not done yet. You need to know what the elastic section modulus of the section is to the tension side. So that means that you need to know if it's negative bending or positive bending at the one location you're looking at. And then you need to look at the section modulus to the tension side. Of course you need to know that just to figure out what VC is. This is what ACI has done. We're not done yet. You need to know what the pre-stressing, the stress in the member on the tension side due to pre-stressing, where external loads cause tension. You need to know the stress due to dead loads only, the stress, the M over S, elastic section modulus, at every location in order to know what the shear capacity of the concrete is. You need to know something called FPC, which is just the average pre-stress compression in the member, just to be able to calculate what VC is. And you're supposed to figure out what the vertical component of the pre-stressing steel is, because the pre-stressing steel will be laid out in a drape. It'll actually be laid out in a parabola most of the time. And you need to know what the vertical component of that is, just to be able to figure out what VC is. Now, I love teaching this class. I love 9 out of 10 weeks of it. I hate teaching. It's ridiculous. There's no way in the world all those things that I just said that we're going to have to calculate. You move over 2 feet, you got to do it all again. And yeah, you're going to do it. We're going to suffer through it together. Like I said, instead of trying to teach it to make you love it, I'm going to teach you to hate it. It's much easier to teach that way. It makes a lot more sense. I got depressed doing this, and I'm not kidding. I was actually going to have my dad come in and teach the week of shear because I just didn't want to. But that's not fair. I'm chickening out. Unless I'm having a nervous breakdown, which does happen to me now and again, I will be here and we'll get through this together. Minus that week, though, I am sure that you are going, if you give me all you've got, I'll give you all I've got, you're going to really like this material. You're going to see what is really wonderful about it. My father, who we're going to talk about in a minute, but he's going to run your discussion, he is a very big name in the concrete world. He was very active in ACI for many, many years, and he taught this course here at UCLA for 16 years in the 80s and 90s. Had I had my epiphany that ACI was very responsible because of all that sheer stuff for the lack of interest in this class throughout the country and throughout the world, I could have gotten to him, and I probably could have influenced him to try to make something happen in ACI. I didn't have my revelation soon enough, and he's now out of ACI. He still has contacts and friends there. And he's a good father. He knows this upsets me, and so he's trying to go and see if he can get anybody's ear who might be interested in changing this. And so far, they're defensive. They love it. This is the way it's been for decades. I think since the 1960s, these equations have been in there. And they're so ingrained, and ACI is just sure that they're wonderful. They're sticking with it for decades more. So I'm just going to keep teaching to students year after year to hate it, and that it's wrong. And if they want to know why this class is so unpopular throughout the country and throughout the world, they can look to ACI shear equations. You know, it's not the only problem, but it's certainly ACI's only problem. If they could fix this, if they'd have fixed this 20 years ago, I think we'd see a dramatic difference in the educational world and the interest in this material in this class. And by the way, the interest in this material is off the charts in practice. You can't go anywhere without seeing prestressed concrete being built. Right now, this scares me. I counted it yesterday and I had to calm myself. But I have 35 active prestressed concrete jobs right now. Active meaning somewhere between just starting to design them and they are just finishing in construction and everything in between. But there's only 2 of us in my firm, so that's way too many jobs for 2 people. So that's, that explains my nervous breakdowns I have every once in a while. My business partner and I take turns talking each other off the ledge. You know, come back in, it'll be okay. Yeah.
You guys hiring?
You know, we're talking about it. The problem is this is such a unique material, and it takes so many years of first designing other materials and then really getting good at this that it's hard, you know, but I'm reconsidering. We're working way too hard. But that shows you how popular this is. I mean, it's not popular in the educational world, but it's popular out in the practicing world. And even the large firms, even Martin's office and Engelkerk's and KPFF and all the really good firms, they only have 1 or 2 people inside those firms that really know prestressed concrete. And you know what? It's kind of the nature of the beast and most people's nature. Do you think they want to share that information? The truth is they don't. You know, my father's generation, there were a lot of good prestressed concrete people. They came out of companies like Atlas and VSL in the 70s. There was a boom in prestressed concrete. But people didn't share that information much. And they didn't go out into the educational system and teach people. They kind of kept it close to their vest. And then they retired. And there's me left to design all this stuff and a few other people out there. So I've decided it's kind of my duty to get back here and teach other people how to do this. It's been great to me, and it will be great, you know, to you if you decide to pursue it. Like I said, had I had my epiphany earlier, I think I could have worked through my father to actually get this changed. But now I'm working through you to get this changed. So. Here's another thing that's just on my mind as I was making up my notes. This is technology. You know, the university systems, UCLA, Stanford, all the good universities. You know, it's where these great ideas come from. It's where technology originates. But it's funny, they don't always want to apply it themselves. You know, the technology is there, they may generate it, but then when it comes to applying it, and I'll tell you what I'm talking about. I know you think your tuition is too high. I see it on TV. I've seen the protests out there. Your tuition is too high. You know, when I was at Cal Poly as a quarter system, my quarterly tuition was $249 per quarter. Basically, $750 to take a year's worth of courses at Cal Poly. In the 1980s. That was 83 through 88, 5 years for me. Then when I went to Berkeley, this was kind of a shock. I actually felt guilty about this. It was a semester system, and if I recall, it was $1,500 for a semester. I'm not sure what you're paying now, but I think you're paying a lot more. Well, my point in talking about that is that, this is the type of stuff that's probably going to get me fired out here, but please don't run and tell everybody. I am being videotaped, so I'm in a little bit of trouble. But there's tremendous redundancy in the academic world. How many people are teaching Calculus 1 just in California? At every junior college, they're paying somebody to do that. At every state college, they're teaching somebody, at least one, maybe more. Every university, you can look in the civil engineering department and strength of materials or statics. There's somebody at every single civil engineering school basically getting paid to teach the same thing that somebody else at another school is getting paid at professor's type level. And please don't run up and tell anybody that I think everybody should get fired. I don't. But I know right here, technology is already available to change that. And it's a perfect storm right now. Your tuition is way too high. Your education's good. Your education's good, but the cost is going up. But if you think about it, you're somewhat restricted in your education. And I took it to heart that Cal Poly stopped teaching prestressed concrete. That was my school. This is where I make my living doing this. And for them to just stop teaching it because it wasn't interesting enough didn't sit well with me. So I offered to teach it for free, and I did last fall. And because of UCLA allowing these videos to be seen by anybody in the world at any time, those students were able to see the videos. I got in my airplane. I flew up every Friday, basically ran a discussion. But it was fascinating to me because they didn't really need to talk to anything. They didn't really need to discuss anything. They watched the videos. They watched it in groups. They paused it. They took down notes off. They backed it up when they didn't understand something. And it was an incredible experience. I had 10 students up there. It was just a trial thing. I talked them into doing it. I didn't talk them into doing it. You want to hear the real story. I tried talking the head of the department up there into it. And he gave me the good lip service that, yeah, no, that sounds good. We're very interested. We're going to talk to people about that, and I'm going to bring that up at the next something meeting. And, of course, it never happened. When do things happen? Things happen when the biggest donor to the school has a son going to that school, and he's about to graduate after never taking the class, never having prestressed concrete. And that biggest donor also made a lot of money in prestressed concrete. So all of a sudden, when the donor talks, the administration listens. So they were interested. And they, like I said, I did it for free. It wasn't free. It cost me a lot of money. Airplane gas is $7 a gallon. And I flew up there 8 times and met with them. But it went really well. They did basically the same class that I taught last year here. And they've actually told me they want to hire me and actually pay me to do it next year. And I think I'm going to do it. I don't know if UCLA's okay with me using their videos, so I'm making my own videos in my office for this. And the point I'm rambling about and getting at is they're going to take this class as an elective. It's available online. The technology is there. There are classes that you could be taking. You're at a fantastic school. John Walls has done an absolutely incredible job building this program since he's been here. It's extremely well respected. But that doesn't mean there's not a good class down at UC San Diego that Bob Engelkirk is teaching, or Graham Powell up at Berkeley, or somebody at Cal Poly. And I would think as elective courses, there may be ways to bring down your tuition and actually open up the world through technology, through videotapes, through online types of courses. I mean, you are paying into the UC system. I think at some point someone's going to ask, why can't I take any class in the UC system that I want? And it's a good question. I mean, I think that time is coming. And again, don't run and tell everybody that this is what I think should happen. I just think I'm just reading the tea leaves. I think it's going to happen. I think the prices are too high, and those are professor fees, to be honest with you. There are ways to have professors teach to more schools, more classes. but not have so much redundancy in the school system that's there. So anyway, the reason that I bring that up is that I think this class is a perfect candidate for that. It's a class that there's no competition. Nobody's teaching it. And I would like to see this class actually taught many more places, not just UCLA, not just Cal Poly, but other places. I would like to teach the whole world. So, they tell you, don't make your aspirations too high because you'll just disappoint yourself. So I'm only shooting for the whole world. We'll see if I'm disappointed. I don't know. I'm interested in your perspective on that. When I was putting together my notes, that happened to be on my mind. But well, let me ask you this. If I'm going to ask you not to be on your phone, I think you probably already know I'm going to ask you that. I won't start texting with my wife or anything back and forth. If you don't, especially with my wife, that would be kind of weird. But for right now, if you've got your phone, if you're interested and you have a Facebook account, if you go on Facebook and you search, it has to be P/T. This is my book. You're not required to get my book, but for fun, I did a Facebook business page, PT Concrete Principles and Practice, and I don't know, one night in a drunken stupor, they asked you, do you want to boost this? Well, I don't even know what that means. I'm a 50-year-old guy. I don't know what boosting is. But I said, yeah. I boosted one of my posts, and it was, I don't remember, I think it was just the one that says, hey, I have a book. And I got some pretty good response back. But then, in a different drunken stupor, I posted that you could take and watch these UCLA videos online for free. Or I said something like, watch my UCLA videos online for free. And they asked me, I put it up there, and I think I got my 12 friends and family who liked it. And for quite some time, I had 12 solid likes. They asked me if I wanted to boost that, and I said, okay, I will. Or again, didn't really know what it means, but they asked me what countries. And I got a globe out. I put in every country that I could see. And, it cost me $150. And I don't know if that sounds like a lot of money. That's peanuts in advertising money. It cost me $4,000 to run a one-page ad in the October issue of Concrete International. So if I want to sell my program or I want to sell my book, I'm looking at spending $4,000 anywhere. So this was $150. So this was okay. Has anybody found that? How many likes does my Yeah, and everybody like it, by the way. No, but the one that says audit my UCLA class. Anybody? 33,000. Now, for $300 to get 33,000 people to take the nanosecond that it takes to look at it and click like, what do you think I'm interested. What do you think they liked? Why would someone take any time out of their life at all and click like on that? Is it me? I've got a pretty big ego, but not that big. They don't know who I am. They don't care who I am. Is it my book? No. I didn't sell 33,000 books. I think what they liked is that a prestigious school like UCLA will take these videos and allow them to see them. I think that's it. I think that's the whole thing. That, I was trending big. Sounds funny to say that. In Indonesia, in Vietnam, in India. I was getting hundreds of likes a day from those countries. And I think it's just people who don't have access to a school like this, but UCLA will allow them to. I think that's pretty incredible. That's what keeps dragging me back here. If UCLA is into and continues to be willing to broadcast this to anybody who wants to see it, I will find a way to get up here. I drive and I hate it. I flew today. It takes me longer actually to fly my plane to Santa Monica and Uber my way over here, but it's more fun. So I did it today. I don't know if I'll keep doing it. Looks like Santa Monica is going to fog over, so I'm probably going to have to do an instrument departure out of here. So it may not have been the best idea for today, but I've put in a request for a bullet train from my office directly up to the campus. I think it's stalled. I'm not sure where we stand on that, but that would be the best. But I'm very proud to be associated with UCLA. And particularly, everybody's proud to be associated with UCLA, but with them doing this and being willing to do this, I will keep finding a way to get up here. If students want me to, I will get here. Okay, the TA for this class. I already gave that away. That's, I'm pretty good at this. If you were asked people around town, if you were asked other professional engineers, they'd probably say that I'm fairly qualified and pretty good at this. There's no dispute, and that may be debatable on where exactly I stand in the hierarchy, but it's pretty much indisputable who the number one person is. And that's been my father for years and years. Now, he hasn't practiced for quite some time, but he's still considered the go-to person. He was very active in ACI right up until, I think, last year or the year before. So extremely well respected. When I came out here in 2011 to teach this class, I didn't realize that Professor Wallace was asking me to teach the last time this course was, this course was ever going to be taught. I'm not exactly sure if I'd have agreed to do it. I probably would have, but I then hoped that it changed. But I had 19 students. The class had been kind of a miserable failure. They'd had a number of people try to teach it, and the 19 students I had were very honest with me. They just needed 4 units or however many units this is. They had to get out, and this was the one that was available. It's always open in space and prestressed concrete. So they didn't cancel the class. The students brought it back. And the next year in 2012, I had about double, some upper 30s. And that was going well. I was very happy, but that was a little bit more stress, a little bit more difficult to handle. The third year, I had mid-40s sign up. And at that point, I decided that it was becoming a lot for me to grade, me to do everything. And I went to my father and asked him if he would consider coming back and being the TA for me. I needed somebody who taught this class before and who had experience practicing. So, and his first response was no. Now, he's got a great sense of humor, and you should probably needle him respectfully about that, but his first response was no. And an hour later, he called me back and said, all right, I'll do it, but certain conditions. I don't do anything, I don't lecture. He laid down the law. And the reason is not that he didn't want to do it, is that you people, all of you people, are very smart. I mean, you're some of the smartest people in the world, and you come from all over the world, and you've made it through a very rigorous civil engineering, very well-respected civil engineering program. And if you've made it to your 4th year or you're a graduate student, you're intimidating. I'm intimidated. If I didn't really know what I was doing up here, and if I was teaching botany, which, I'd be nervous. But luckily, I feel pretty confident in my abilities to at least teach this one topic. But he was nervous, and it is intimidating. But it took him absolutely no time to get back in the swing and realize that he's still the sharpest person that I know. He's still the best resource on this particular topic, and he has really enjoyed coming back. The response, but I had to inch him along into doing a few more things. How about, would you just consider doing this? Okay, I'll do that. So the agreement that he and I had for the last 2 years was he was just going to redo the homework assignments, and that's what he did. He just redid the homework solutions for everybody, and sometimes he'd show a couple different ways to do it. But the responses I got back in the evaluations were that, I'm not using him to his potential, and it was frustrating for students to go for 2 hours on Friday and just re-see the homework that they'd already done correctly. And I kind of got slammed a little bit, and rightfully so, and it was valid. And I took it to heart, and I'm trying to improve the course every year. So he's got an entirely new role that he's agreed to this year. I kind of had writer's block. I've already made up all the homework. I've already made up the midterms. I've already made up the project you're going to do. I like to get out ahead of things. But I kind of had writer's block in the midterms. I'm trying to find different ways to there's only so many things that we're covering on the midterm, and kind of get stuck finding new and creative ways to ask about it. So he taught this course for 16 years, so he went back, pulled out some of his midterms. We kind of started with that, and then I added something, we tweaked back and forth, but we've come to this, we've come to equilibrium on 2 midterms. We've both done them. I did both in about 45 to 50 minutes, which is what I shoot for whenever I make a midterm for myself, and I give you 2 hours to do it. I think that's fair. But I will be honest with you, these 2 midterms are more aggressive than I have been. They're a little more challenging than anything I have given. And there's always a few people who are a little bit panicked. There's some people who got a hold of your last midterms, and I feel like they have an advantage. Well, get a hold of my last midterms, study them, learn what I was doing. You'll learn something. It won't help you in this midterm or the next one, but you'll still learn something. So I still think you should hunt them down and figure out how to do what I asked. But the way you're going to get helped on these midterms is going to the discussion. Now, no new topics will be presented. That would be unfair, and I know not everybody can make it to the discussions or wants to. But I'm going to lay out the topics. I'm going to give the same lecture right out of my book that I always do each year. I'm going to present it, try to make it more interesting and keep myself entertained while doing it. But he is going to do examples much more similar to what you're going to see on the midterms. So every Friday will effectively be test prep. So if you've had trouble on the homework, you need to come to me in the office hour, or you can come to my father. I will have office hours. I'm shooting, back in the civil engineering department, 5732, back in that corner. It's kind of a miserable room. I always migrate out of there and go to the front and sit on the couch, and that annoys everybody else, but I kind of do it on purpose. Until they can come up with a better office, at least has some air circulation in there. But I do something, I don't know if you've talked to people who've taken this class. My goal is to teach you how to do this. My goal would be, as if you were going to come and work for me, I would want you to know what you're doing, be ready, and be prepared. After being in the industry for 26 years now, I just don't see things the way the academic world does. I'm not interested in finding the 10% best and then the next chunk and do a bell-shaped curve and making sure that 10% get terrible grades in the class. I would like everybody to do well, and I really mean that. And I'm going to be giving it all I've got. And if you want to learn, every one of you, I will take everybody across the finish line, and everybody can get A's. That's, again, a couple of years ago, they had to talk to me. They said that the grades coming out of this class were too high, and I needed to make this class more difficult. Now, I argued, and I made the class more difficult. I did what they asked, and the students just stepped up. They just, I raised the bar, they raised their level. And I keep raising it. I'm raising it again in the midterms this time, but I'm very confident, especially with those of you going to the discussions, you're going to raise your game too. And what I concluded and what I told the school was I consider myself one of the best at this particular material. And I do this every day of my life. I have 35 active pre-stressed concrete jobs right now. I taught out at Cal Poly Pomona in the 90s for 4 years. I taught at UCI. I have teaching experience. But I think, you give me some of the best, smartest people in the world who've gone through this program, combine it with me and the fact that I know how to do this, and all I'm trying to do is teach you as if you worked for me how to do it. There's no reason you all shouldn't do extremely well. And that's what I told the department. I said, that's what I'm here for. I'm going to try to teach everybody to be prepared to go out and sit at a desk and tell your boss that you are enthusiastic, energetic, and ready, technically, to take on a pre-stressed concrete project. And that's my goal. It's not to create a bell-shaped curve. It's not to wipe some of you out just because there should always be 10 or 20% who don't do well in every class. It's just not, it's just not in my nature. I'm going to try to help every one of you, and you guys will. I never do give all A's, but I give some pretty high grades. The people who have struggled in my class, and you can decide if this is you, has actually been some of the master's students who got wind that grades are pretty good in this class. This is an undergraduate course. They're just going to cruise through it and take it easy. Those are the ones that a few times I've had some real struggles with. At the end of the quarter, they have not done well. They're looking at C pluses and B minuses, and I'm saying, look, it doesn't matter if you're an undergraduate or graduate. You're getting graded exactly the same way. I don't treat anybody differently. There's no different grading system for graduate or undergraduate. But you got to work hard with me. I'm going to work you hard. I'm going to give you 6 homework assignments. Those are not particularly difficult until you get to the shear. The midterms will be challenging, but you've got probably the best technical person in the world showing you, and he also helped make up the test, showing you how to approach the test. So you've got, really good tutor. And the project will be challenging. And what will happen is I will give you that shear assignment that's going to be miserable and take a lot of time. Right about the same time you have midterm number 2 in the 8th week, right about the same time you are waist deep in doing the project. And master students are often taking Tom Sable's course too. And they're doing very similar, difficult, challenging, time-challenging things in that class too. So those people have suffered. And I'm just warning you. I'm just telling you that that's a potential. If you're taking this class and think it's going to be something you can just cruise through, we start off pretty, not too slow, but we move into it. But by the time we're in the 8th week, you have a lot to do. And if you haven't been up, I told you, everything circles back around in the project. So if you really didn't understand what you were doing on some of the homework assignments, you're going to struggle probably with that same concept as you try to do the design project. So anyway, that's only a very few people that ever happens. Most of the time, I get great energy, I get great dedication, I get lots of emails. I will take 10 weeks and basically dedicate myself to this class, and I will answer emails at 6 in the morning, 2 in the morning, whenever I'm up, I will check my emails, and if you've got a question, I will try to answer that, and that almost happens around the clock. But I will also have office hours Tuesday, Thursday. I'm shooting for 2:30 to 3:30. That's something different. I'm trying to straddle 2 different hours so that I don't want to just be 3 to 4, so anybody who has a class 3 to 4 can't go to the office hours. So I'm trying to be in 2 different hours. So plus or minus when I can get here, 2:30 to 3:30. Father's office hours are going to be Wednesday, I believe 10 to 11. He will clarify that on Friday. But between the two of us, I'll be here Tuesday, he'll be here Wednesday, I'll be here Thursday, he'll be here Friday. You've got Tuesday through Friday to have direct contact with us. I think I started to say this and forgot where I was going. I bring the homework solutions with me on Tuesday. He will bring the homework solutions with him on Wednesday. You are encouraged and you will benefit. If you start the homework over the weekend and by Monday you've finished it or made tremendous progress, I want you to come to the office. I want you to lay out what you've done. I'll lay out the solutions and you can see what you've done. You can see where you're at. And I may grade it right on the spot there. We're going to try to use the Turnitin system. I have never used that before. But because of my experience at Cal Poly, having them PDF all their homework to me, I was able to grade it and just email it right back to them. I'm a big fan of doing it on the computer and online, so we're going to try that. Have you guys done that in other classes? Okay, well, we'll all try it together. If it doesn't work, we'll go back to the same. Everybody rushes up here and puts this big ugly pile right here. And but I because the class has grown and because I've got so much of my own actual design work, I have asked for 2 TAs to help, and my father's going to grade. I'm going to try to oversee the grading. I'm going to try to go online and watch what's happening as it gets graded, but not do it myself, unless you bring me your homework on Tuesday, and I will grade it on the spot. We'll look at how you've done. If it's all done, it's all correct. I will grade it right there. You scan that, and I'll sign it, and I'll just see that you've gotten all 10 points. Same thing can happen on Wednesdays with my father. He will have the solutions. I don't bring the solutions, or I don't show the solutions on Thursday. That was kind of a disaster when I did that. I get people rushing in with 15 minutes left to go, trying to take down and erase, and then they're working on it in class, and they come running up late. The reason that I bring the solutions and let you look at the solutions is because I'm rewarding you for doing it early. You know, the world will reward you for doing your projects early. Nobody at your job will ever like the person, the guy, the girl, who always pushes it to the last minute. You stress everybody else out. You know, you're working as a team. They've got 2 draftsmen, you've got 2 engineers, you've got an overseeing boss, and you've got deadlines. And boy, do I know about deadlines. You know, we've got a 50% design development submittal. We've got 100% design development, 50% contract document submittal. I mean, I've got my calendar just filled up. And if you're one of those people where everybody else on the team got their stuff done and you're just barely getting in there an hour before submittal time, and all of a sudden you got to go to plot, and you'll make everybody else tense. So the world rewards those who just get on their stuff and do it early. And so I'm going to try to reward you for that too. Okay, the syllabus. The syllabus has been posted. The important thing in the syllabus is that the homework is worth 15%. Each midterm is worth 20%. The thing that I personally enjoy the most is the project that you're going to do. I think you will benefit the most from it. Homework is homework, and you know, we all like homework, and you're proving to me that you understand the concepts and proving to yourself. This project has proven to be even more important than I thought. Students are taking it to their first job interviews, and I promise you, you can take a steel project to a job interview at KPFF or Engelkirk or Martin's or, you know, SGH or any of the big firms, and the chances of you sitting across from the person interviewing you and knowing more than they know about that particular material are very slim. Something would be wrong if you knew more than they did. But you're basically saying, I'm competent, I'm ready to start, I'm ready to learn, I've done some steel, I've done a steel project, I've got the fundamental framing ideas down, and I can design beams and girders, and I know what a composite beam is, and you know, I'm ready to take a job and then learn from that point. The interesting thing about the project that you're going to do in this class is you very well may know more than the people interviewing you about this technically. And that is what's happening. That's the feedback I'm getting. They're taking this project, laying it down, and the people interviewing them are going, well, okay, what did you do? How'd you do that? And I mean, I don't want to ramble for too long, but one girl who took this course did very well on the project, went and had just a summer intern at John Martin's office. John Martin's office is the biggest office in Southern California. I mean, they're the biggest structural engineering firm. They did the Staples Center. They did the MGM Grand in Las Vegas. You know, I worked one summer there. I was also an intern there, but I was only 2 years into school. But she graduated. She was between, you know, undergraduate and going off to graduate school. And they asked her to actually give a presentation to 100 engineers using the project and explaining the process of designing a post-tension concrete multi-span beam. And she did it. And I would have been nervous if Martin's office asked me to go and walk them through, you know. Probably not, but I had a few butterflies. But basically an intern who'd never really had a design job, who was taking a summer job between graduate school, undergraduate school and graduate school, doing that, That was incredible. But she's not the only one. People are interviewing, saying, hey, we want to hire you. And not only do we want to hire you, we want you to become our technical person on prestressed concrete. And I don't know if you're aware, but your education doesn't stop when you walk out the doors of UCLA. Your education continues within a firm, and the better firms have great internal education systems. They have lunchtime seminars. That's the way new codes are implemented. Somebody goes, learns all the things in the new code, and teaches everybody else in the firm. They come and 1 hour, they buy pizza, and everybody sits there and learns about the new code that just came out. I mean, that's how you have to. You constantly have to keep learning. And there's a big transition from allowable stress design of steel to LRFD design of steel when I was a young person. And it was lunchtime seminars of, going through, this is how a girder is designed, this is how a composite beam is designed now. And you constantly have to teach yourselves, teach each other. So, my point is that this project has proven to be pretty valuable. I always thought it would be very valuable when you go out to take your PE, kind of maybe your PE exam, but definitely your structural exam. There is usually a pre-stressed concrete question on the structural exam. They give you an option of reinforced concrete or pre-stressed concrete. The pre-stressed concrete, most people have never had it, so they're terrified and don't take that option. But it's usually very easy for anybody who has had the class. So I always said, take this, don't throw it away. Take your project and save it 5 years, and when you go take your structural exam, bring it along. But it's proving to be valuable much earlier than that. Okay, and the final will be 15%. I take my foot off the gas a little bit on the final. The only problem with doing that is people misinterpret that as meaning that the final is very easy. And I've had some people going in with solid A's and getting 70% on the final because they just thought that because I made it 15% that it was just going to be very easy. And then their A went to A-, and I end up feeling terrible. So don't make me feel bad. The final is 15%. I am somewhat taking my foot off the gas on it, but you still have to study and work hard. Okay, I think I emailed out to everybody about the book and where you can find it. If you want to. I wrote the book to change the world, to give all the other academics. The idea was once they saw my book, they would say, oh, this is so wonderful and easy. I'm going to rush out and I want to teach pre-stressed concrete all across the country and everybody would love it. That didn't happen. I contacted about 24 people that I found that were actively teaching pre-stressed concrete in some major university throughout this country. And I sent them a free copy of the book. The book cost me $80. I have to pay $80 to get the book. But it was worth it. I sent it to them. And I thought, maybe half would take the book on, teach from it, see the value, see the wisdom. I'd start this big wildfire of pre-stressed concrete love. Didn't happen. In fact, not one of them picked it up and decided to use it. In fact, they criticized me, told me that, well, we do pre-tension concrete, we do bridges, we do something else. And I said, my book's fine for that. I do pre-tension concrete, I do precast. It's all that, it's all in there. But my method of teaching this class in an aggressive way and multi-spans and forcing, giving you a tool to be able to analyze multi-span systems, that I just got resistance. I just got people fighting me on that. And finally, Cal State LA decided to pick up the book. They are the only people in the world, other than me, at this school who use this book. Anyway, you don't have to buy it. I literally, if you're one of those people that can't stand that the teacher has published a book that's exactly their notes and they're putting their exact notes from the book up on the board, then don't buy it, because that's what I'm going to do. They're my notes, I like them, and I wrote them, and if I didn't like them, I wouldn't have put them in the book. So some people like having a nice, crisp, clean copy and sitting there and just listening to what I have to say. Everybody learns differently. You know yourself best. Do whatever you want. I would prefer, given the choice of you not showing up a lot or not paying attention and buying the book, that's not my first choice. My first choice is you don't buy the book. Come, pay attention, take great notes. That's all you need to do. You will be very successful if you just do that. Funny thing is, I've sold a lot of books, but not to the academic world. The practicing world, the first 7 or 8 chapters are really meant for the academic world. After that, they are design problems really coming right off our desk, showing practicing engineers how we design various elements, mat foundations, seismic diaphragms, beams, two-way slabs, one-way slabs. And the practicing engineering world is eating it up. In fact, that's why S.K. Ghosh, you may or may not have ever heard of him. He is kind of the world authority on code, everything code. He knows every code revision, he knows why, he knows how it's interpreted, he knows what's coming, he knows, and whenever code change is happening, everybody rushes to S.K. Ghosh seminars and listens to what happened, what do we have to do now? Well, the truth is they send 1 or 2 people from a firm, and those 2 people go back and teach the other 30, so that is how it goes. But he's a terrific guy, and Susan Dowdy is his partner, and we've kind of teamed up. They distribute my book now, and they also sell our computer programs. So if you want to, that's where you would purchase it. It's the cheapest places to go there. That the price actually includes the shipping to you. But like I said, just come and take great notes. That's all you need to do, actually. So, any questions? You guys always start off so quiet. By the 3rd week, I get all kinds of noise out of you, but nobody wants to start. Okay. If there's no questions, I must be remarkably clear. Yeah. PTE number? All you have to do is email me your student ID number. There are 15 open spots. Against my wishes, I should turn this off. They bumped the class size from 35 to 60. And I had always allowed more people in, but I was really considering lopping it at 35 this year just because of my personal workload. And they said, no, we're UCLA. We're going to do what we want. You're going to go up to 60. So I will go up to 60. John Wallace is great. He gave me 2 TAs, lots of grading help. I'm going to have all the help I need. So it's all going to work out good. But I will stop it at 60. So there are, right now, I think there are 15 open spots. So I don't know if we'll even get there. Okay. What is prestressed concrete? I'm just going to give you, you can take notes on this or not. You can just sit and listen. When I was your age, just about every material was taught in what was called working stress or allowable stress. Do you guys even hear those terms? I expect you don't, but concrete was the only material taught in nominal strength, what then became load-resistant factor design. That's because concrete, ACI has always pretty much led the world. They always came up with the most creative new things because the fierce competition between steel and concrete has always been there and will always be there. They're always trying to outdo each other. They're always trying to up one another and fight for, office buildings should be done in concrete. Oh, they should be done in steel. Here's why steel's better. Here's why concrete's better. But concrete led the way a long time ago in nominal strength. So this idea of coming up with load factors on loads, actually calculating the nominal strength of a member, comparing that using a capacity reduction factor, that was actually extremely unique only to concrete when I was your age, when I was in school. Steel was done what was called allowable stress design. Wood was allowable stress design, and masonry was just transitioning into nominal strength design. Now everything is nominal strength design, and because of that, you guys don't even know what I'm talking about when I say working stress or allowable stress design. That's important because pre-stressed concrete, which always scared the pants off everybody, it's either just not well understood or just scares everybody you're putting so much force in. Pre-stressed concrete from the beginning of time has always had to satisfy both allowable stress, a complete allowable stress design, and then a complete nominal strength design. You know, and that's the way it is today, and that's the way it will probably always be. So I need to introduce a topic called allowable stress design. Used to be easy because everybody knew what I was talking about. Now it's the only material left with an allowable stress design. But effectively, under allowable stress design, you put on the loads that you really believe to be there. You know, if the code says parking's 40 pounds a square foot, you put 40 pounds a square foot on. If you calculated the dead loads to be 85 pounds per square foot, that's what you put on. You put on the member. It effectively was analyzed through elastic section properties, and you checked stresses. You know, we checked the stress in steel back in my day. We didn't use a Z, we used an S. You know, Z being the plastic section modulus, S being the elastic section modulus. We were doing S's. We were doing everything elastically except for concrete. The world has transitioned, but still, pre-stressed concrete has both. So we will spend the first half of this course, really, your first midterm will be entirely on the working stress part of concrete. We're going to put the real loads on, not factored loads. The factored loads you never expect to get there. Something has gone very, very wrong if the 1.2 dead and the 1.6 live in steel ever actually gets there. Those are your safety factors. And the most load that should ever get there is 1.0 times dead load and 1.0 times live load. 50 years of that building, that's the most that should ever be there. But you have to have factors of safety. So that's what the load factors are. Allowable stress design says we're also going to look at the structure under the loads that are really there, day in, day out, the loads we actually believe to be on there. And we're going to have to make sure that the stresses in the material maintain some level or below. And in concrete, it makes sense to limit that stress to what? What do you think? What do you think makes pre-stressed concrete cool? What stress would be the line that we don't want to cross in concrete? Concrete loves being in compression. Be in compression all day long and be happy the rest of its life. What does concrete not want to be in? Okay. Doesn't want to be in tension. We could design pre-stressed concrete to keep concrete never in tension if we wanted to. That's unnecessary, though. That would be very expensive. It would not be an efficient use of the material. So what's the actual line, do you think, that we're not going to want to cross? What's the next thing? We'll allow some tension. What do we want to try not to allow? Cracking. So we're going to attempt to design pre-stressed concrete, and that's what you're going to do for 10 weeks here. We're going to attempt to design at least the first half of the class in the allowable stress part such that under the real loads, not factored loads, not the catastrophic loads that's never going to happen, but under the actual loads that we think are actually going to be on the building, we are trying to limit the stress in the concrete to below cracking. So kind of a sales pitch in pre-stressed concrete. Don't ever tell people it's crack-free because for other reasons it will crack. There's a whole bunch of things. But to the best of our abilities, we make a good college effort at trying to keep it from cracking. So that'll make up the first half of the course, the first midterm. I don't have to explain to you what LRFD design is. All the materials now, even wood. We never thought wood could ever go LRFD, but they were the last ones standing out there not going LRFD. So we want to also. So they did. But so now everything, even wood, has got an ultimate strength, and it's much better. I mean, the idea was, back when I was your age, we never knew when it was going to fail, and a lot of times, for design, that's one thing, but because of the cyclic nature of the industry, you go through design bursts, and then design slows down. The cities have kind of overbuilt, but now these old buildings need to be analyzed, so you need to go in and analyze them, and it was tough for young engineers to go in and analyze a building, particularly in seismic country, because you never really knew when something was going to fail. We kept things at the very low elastic level of stress. We never got near real yielding, real plastic behavior or anything. So the very good thing that happened in the industry is all materials are now analyzed based upon their failure. You put load factors on for the factor of safety. Capacity reduction factor gets put on the capacity of the structure. And you promote things, flexures usually, you want flexure failure, so we give it a 0.9 usually in most materials. And we don't want shear failure, and we don't want axial failure in columns, so those get low capacity reduction factors. So somewhere between the load factor and the capacity reduction factor, you have a pretty good factor of safety against failure. And that's, again, that's been good. We will do that too. This is one of the more difficult things that will happen. I will spend about 4 weeks talking to you about service level stresses. We'll check cracking. We're going to do elastic section properties. You're going to be doing moment distributions based on elastic section properties. And then we leave that behind. We just dump it because that's what the code says to do. That's what designer pre-stress, and we start over. Then we put 1.2 dead long and 1.6 live, and we start over. And we go to the Whitney stress block, and we do crack the member. Because at failure, it will crack. Even pre-stressed concrete will crack. We only try to limit it to not cracking under the everyday average loads that we expect. But then we still have to say, in grotesque overloads that we never expect to happen with these large, 60% greater live load than we ever anticipate, we've got to make sure this doesn't kill anybody. And we'll go through that. And it's, for some people, a tough transition after we spent 3 or 4 weeks talking about an elastic behavior of a material under actual real loads to go to the concept of factored loads, which are not real loads. Those are pumped up loads that will never be there unless you've had a bad day. And looking at the capacity for failure. So we're going to do both. First midterm will be entirely based on the elastic section properties, stress design. Second midterm will be on strength and failure design of this. You're going to learn both. It's great, and it's always been great about pre-stressed concrete, because if you really spent the time to learn about it, you understand the material's behavior under realistic loads, and you understand how it's going to fail. And you've always had that in pre-stressed concrete. The code is actually trying to punish them, but what they made were better engineers by doing it, because those of us who spent the time really do understand the material from no load, light load, medium load, heavy load, failure load. I can tell you what pre-stressed concrete is doing anywhere along the line. Okay. I've been throwing out terms pre-tension, post-tension, pre-stressed concrete. Pre-stressed concrete is an umbrella term. It captures some subsets of what are pre-stressed concrete. Okay. Pre-stressed concrete means this is concrete that with high-strength steel we are pre-stressing. We are purposely stressing the material on the first day of its life before any actual loads get applied to it. So we're taking the active role. We know loads are coming, and we're being proactive. We're actually going to stress against those loads. We'll come up with a term called balance loads. We're actually going to offset the loads. By pre-stressing, we're going to do the opposite to the member that the gravity loads do. That can either be pre-tensioned or post-tensioned concrete. The pre and the post entirely strictly mean relative to the concrete being poured. That's all that means. If you write that down, that's all you need to know. Pre-tensioned concrete means the high-strength steel is stressed prior to the concrete being poured. Post-tension concrete means that after the concrete is poured, the high-strength steel will be stressed. Pre and post. Entirely related to when the concrete is placed. I've just said you stress the steel before the concrete's even in town, before it's even anywhere. Yes?
For post-tension concrete, does the concrete have to be cured?
It has to be cured enough. If it's still soupy, not much is going to happen. Those anchors are just going to shoot in. But yes, it has to be cured enough. In pre-tension concrete, that's really, for all practical purposes, pre-tension concrete is precast concrete. Means it's done in a precasting plant, it's done in a bed. To stress steel, it needs to be stressed against something. You can't just stress steel and have it hang out in air. It has to be anchored off, has to be locked off. If you're going to put huge force into something, it's got to lock itself off somehow. And that mechanism is a stressing bed. So in a precasting plant, they'll have these big steel beds. They will place the steel. And the steel effectively wants to be in straight lines. I mean, steel is just like a clothes hanger. You're going to think about that all course. As it's trying to straighten it, as it gets stressed, it just wants to go into a straight line. Now, in pre-tension concrete, you hold it down at various points, so you create what are called kind of harped profiles. So precast concrete, the steel often looks something like this or like this. But, these are anchor points where it's been held down to kind of change its direction. In post-tension concrete, we're talking about cast-in-place buildings. So we can lay the tendons in any profile that we want in cast-in-place concrete. They'll get placed in the forms really in any shape that we feel like. And they'll just lay there. Once the concrete gets poured and cured, that will lock in the position of the steel. And the concrete starts curing, it starts hardening, it becomes a very stiff element. Then when you try to stress it, it can't straighten out. What it tries to do is react on the concrete. So we'll often use a parabolic profile. In fact, just about everything we're going to do in this class, it'll typically be a parabolic profile. And that profile will push up on the concrete element, try to straighten out. Steel's just in your mind, every one of these is just trying to straighten out. That's all pre-stressing steel is trying to do. You can put it in any shape you want. In a precasting plant, you have a heck of a time putting it in a parabolic shape because you'd have to hold it down every, a million places. So they hold it down in a few places and then stress it, and it takes on that shape. Pre-tension concrete, again, is precast. Oftentimes bridges are pre-tension. They are precast. The element's effectively built in a shop somewhere, and then kind of like steel is. It's fabricated someplace and then shipped. This is my world. My entire world is post-tension concrete. And the differences are, if you do the design of precast concrete, you either work for a precaster, a supplier. Your one job is to work for that supplier of that concrete, or you work for a bridge specialist firm. Now, if those are highly specialized things, and if you've taken that choice, you're no longer really a general practicing engineer. You're not going to be designing steel buildings also at the same time you're designing concrete. You're not going to be dabbling in a lot of different materials. You're probably not working at a Martin's or Engelkirk, KPFF, one of the general design firms. Those firms will do this. Post-tension concrete is what general design firms do, what practicing engineers who may also do other things do. Now, I'm a specialist in this, and I tried being, when I started my firm, I wanted to do steel, I wanted to do some wood, I wanted to be a very general firm. It's very difficult these days to be a general practicing engineer anymore. The world just kind of forces you to specialize, and You know, when I was your age, the entire code was about that thick, and I should probably bring that in. You know, now we have volumes of codes, and the code references other codes out of it. You almost have to become a specialist now. It's too difficult to know every exemption and footnote and every material throughout all these volumes. So, well, probably the best way to show you what this is actually to do my PowerPoint presentation now. Your first homework, the first thing I'm having you do, largely because everything has gone LRFD, you've kind of left elastic section properties behind. And I've found that no matter how smart you are, you get here, and if it's been 4 years since you've calculated moment of inertia and a section modulus to the top and a section modulus to the bottom, you're a little weak on it. It's been a while. So I'm having you just brush up on that. I'm not going to do an example. There's an example in my book, but on Friday, my father will do kind of a refresher on elastic section properties. And those will be extremely important for the first 4 weeks. And you're going to have to get back up to speed on the stuff that you probably learned as freshmen and haven't seen much of since then. But that's just calculating a moment of inertia of a section, calculating section modulus. We need that badly in what we're about to do. So I'm going to skip that. I'm going to go to this. While that's warming up, does anybody have any questions? I know you guys do. The only email I really have is dirk@senecastructural.com. I mean, that's my work email. That's the one I check. That comes on my phone. I may have a UCLA email address that I don't even know about. I don't know who's been sending stuff there, but I don't get that. It won't come to me. It's a little bit dirty pool. I show you this today, not with the intention, but I've learned that this will frustrate you. You know, I'm going to be going through slide after slide, showing you construction projects. Most of them are mine, and kind of rifling through, and you will get frustrated. You know, it's going to be, it's going to look a little overwhelming, but that's okay. Then I teach you for 10 weeks how to do this. I am going to set up, I don't know if I'm going to attend it, but I'm going to set up a job site visit that at least my father will go to. Previous years I've had jobs that are very close to here. Right now the closest I've got is Glendale, but it is very far from me, from Laguna Hills where I live, to get to. So my father's great. He does all of our structural observations in Glendale and Northridge and the jobs in Oxnard that we've got going. So. But anyway, if you're so interested, it's not a requirement of the course. There's no plus or minus to going, but if you want to see one of my jobs in construction, you will have the opportunity to go see it. And then the Friday after the midterm, the first midterm will be on the 5th week on Thursday. The 5th week on Thursday. The second midterm will be the 8th week on Thursday. But the Friday after the midterm, instead of going to discussion, I am inviting you, like I do every year, down to an externally post-tension job that I have, and I've got pictures of it here. For those of you who want to come, it's been pretty successful in the past. It's kind of a hike. It's down to the Coronado Apartments in Newport Beach. Kind of a nice place to be if you've never been there. But we did an external post-tensioning job on 2 very large parking structures there. And the neat thing about it being external is you can see it. It's outside of the concrete. When you get really good at doing this, you start putting it outside of the concrete and fixing and repairing buildings. And that's kind of a specialty forte of ours. But the most fun on that day is that after we go look at that, I'll show you the drawings. You'll get to see how we present a set of drawings, get to walk through plans, sections, details, elevations, shear walls. We had to do a seismic upgrade on it. We had to add foundations. But it's still fairly simple. And the thing is, you can look right up at it and see it. So see the drawings look like the building. And then we go to Joe's Crab Shack after that, and I introduce most of you to your first steam pot. If those of you are not crab fans, probably my favorite food of all time. And If you think of me for nothing else after this class, it'll be the person that introduced you to loving crab. So we'll do that. My point, my long exhaustive point was, you're going to be frustrated with this. You go see a job of mine, a lot of things will get clarified. You get to ask all kinds of questions. Come down to the Coronado Apartments, ask a lot more questions, see our drawings. And by the 10 weeks, I'm going to show you this on the last day of class 2. And you will realize how much you've learned. Sorry. So I found that you will ask very few questions during this. That's okay. On the last day, I can't shut you guys up. You know, there's, what is that? What's that? It's, you know, like, why didn't you ask me these questions the first time you saw this? Okay. This is a job, actually, I think this one's in Buena Park. This is a column, no big deal. This is waiting for a beam. And you are going to design in your project a 2-span beam. It's going to look very much like the beams I'm about to show you. But this is how it gets constructed. The column comes first. There's a cold joint at the bottom. The steel beam form will fit right in there, and that beam will be coming out at us. I like this. I'm not doing much anymore, but for a long time in my career I did design build, which meant I worked for contractors. And on this particular job, this is a big one in Buena Park. It's called the Source. I don't know if it's a huge development. Well, we got the big parking structure in there. And you'll never guess who the contractor was. Who got that? Bill Klorman. Puts his name on everything. You can't drive by that site without seeing his name about 50 times. Good friend of mine, wonderful guy. In case anybody steals his forms, everybody will know where those forms came from. But no, he's a brilliant contractor and advertiser. This is a ramp. We're actually there building the forms. This is the plywood forms going on those steel beam forms. This is the ramp that's going up. That's why you can see all those. But they're right in the middle of placing all of the plywood to make this ramp. So after this gets formed, this is the plywood. You know, we pre-stress lots of things. We pre-stress everything we can. This is the slab. This is the red. You know, I don't see colors well, but I know that that's red. Is the slab pre-stressing steel? It's post-tension. It's actually in plastic sheathing, and if you come down to Coronado, you'll see it in plastic sheathing. You'll be able to touch it. It's dirty, but you'll get a good feel. We wrap it in plastic, and I'll show you those pictures in a minute, but the steel is actually inside the plastic. We want it to be able to move freely. It's greased, and the sheathing may bond to the concrete and will, but the steel inside that sheathing kind of moves at will, and that's how we're able to stress it. The steel will move, the concrete won't. So there is no compatibility like you're used to, strain compatibility in post-tension concrete. You know, you're used to strain compatibility in reinforced concrete because it's bonded. Post-tension concrete is not bonded. Makes it more difficult to understand and confuses people, but it also makes it great. I mean, that's what, by unbonding it, we're able to do some pretty incredible things. So these are the beam forms. These are steel beam forms. That's a girder. You know, these are the columns. The slab is post-tension, and if you can see, the beams are post-tension. And this is actually what you are going to design in your project, is a 2-span beam with draping post-tensioning steel. That's a close-up. In this particular case, it's a different job. The post-tensioning is black. Every supplier has their own color. It just differentiates them. There's no difference between a red post-tensioning table and a black one or a green one or a blue one. It just depends on who made it. You know, so everybody knows DSI makes the black cables, and Millennium puts out the red, and you just know by looking at the color of the steel who made it. But this is a joint. You know, we will take the post-tensioning steel high over the support and then drape it down in the saggy span where it wants to droop, and we will stress it, and we'll want to lift that beam. This is looking right down the beam. I'm actually straddling it, taking this picture right there. But you can see this steel low, and then it's making its way up and splaying out at the anchorage zone at the column. And of course, this is the slab also post-tensioned, high over the support, low in the span. That's the way you would want to drape it, because that's the way when you stress it, it's going to try to straighten out. And when it tries to straighten out with stiff concrete, that lifts that concrete. You know, we're shooting for not only compressing concrete, but keeping it flat. And that's what's kind of amazing about particularly post-tension concrete is we can effectively walk away from a building that doesn't deflect. It's damn near flat, straight, compressed, and almost crack-free. And I'm in salesman mode, it's less expensive. There's less concrete and there's actually less reinforcing. So why isn't every building pre-stressed? That's a great question. They all should be. They should. You know, I am baffled by why any building is reinforced concrete, and I really mean that. I've been designing out on my own. I left since 1997, the end of 1996. I've never designed a reinforced concrete building because I had the option of designing a post-tension concrete building using less concrete. It's less expensive, and it performs better, and it's almost crack-free and it's compressed. So to me, it's always pre-stressed. If it's really small and I'm doing somebody's garage or something like that, maybe not. But I've done a few things for friends. So this is an intersection at a girder. You know, there can either be a column supporting a beam or there can be a girder supporting the beam. This is a big parking structure, so they couldn't have a column here because that's the drive area. You know, you're looping around, circling around in a parking structure. You're always going under a girder. From now on, you guys should never be looking at where you're going. You should be looking up at the framing. That's what I do. I'm surprised I haven't gotten in any accidents. This is the anchorage zone. These are the tails. They're just sticking out of the forms. You know, this is just draped in there. There's no stress in it right now at all. It's just laying in there unstressed. It will not even think about being stressed until after all that concrete is poured and cured. We may specify 5,000 psi concrete, but we will let them stress at 3,000 psi in 3 days. So we use what's called high early concrete. That concrete accelerates very quickly. They will pour it often on Thursday, and on Monday, I mean, this is all around the Southern California area. They're pouring post-tension concrete on Thursday everywhere, and they're stressing it on Monday. That is the typical cycle of basically every job I've ever worked on. So Thursday is a big pour day in the Southern California area. But it's just sitting in there. These are pocket formers. You have to create a pocket so the jack that I'm going to show you can get in there and stress on it. But we leave a tail hanging out there so the jack's got something to grab. You know, here's a beam coming in. The tenons have come up high and then they've splayed out. And there are anchors over here, and this is hanging out of the backside of a column. This is a job called Midtown Crossing. It's actually, I think, 450 West Pico. It's not far from here at all. It was kind of fun. I think this was 2011 that this was being built, and I was teaching this class. So I actually brought a few students over to see this being done. But I would actually just take pictures and then stick them in and bring them to class. I think it's a big, you know, there is parking, there's retail up on top now. There's a big Lowe's and a couple department stores next door. This is after the concrete has been poured. It's hardened. The tendons have actually been stressed. And there's no beam form there. So once that thing is stressed, this is the amazing thing about pre-stressed concrete also. Not only is it cheaper, not only does it come out with a better product, you can pour it on Thursday, stress it on Monday, and strip all the forms Monday afternoon. And that building stands there. It is standing up, holding itself up. In reinforced concrete, how long, it's okay if you don't know this, but if you want to take a guess, it's fine. I don't expect you to know the answer. How long do you have to leave the forms in there before it's safe enough to pull them down and that structure won't collapse? Most people say about 21, 28, yeah. If you got aggressive with the strength of the concrete, maybe 14, but most likely the typical answer is about 21 days. So And if you've seen forms in a concrete building, you can't even walk through that. I mean, there's nobody who can be doing anything. They can't be finishing concrete. They can't be striping. They can't be working, doing anything in there. It's a jungle of forms. But pre-stressed concrete, we stress, we pull. I mean, 4 or 5 days later, you have free access underneath to start all the other trades, mechanical, electrical, plumbing. The guy's got to paint the stalls. The guy's got to put in carpeting if it's a bank. Whatever it is, they have free access to it. Another one of the many amazing things. This is a seismic shear wall. California, I told you become a specialist. I'm a specialist in pre-stressed concrete, particularly post-tension concrete. We're all specialists in seismic design. Every structural engineer in California is a specialist in seismic design. You have to be. So that's a shear wall. That's a pocket waiting. Actually, I believe this is waiting for a girder, and these are waiting for beams to come in. But we give them a nice pocket to come and rest in. People make mistakes, and I'm running into this a lot when I'm dealing with some of the code things that I try to review examples done by academics and code people. And I can't tell you how often they forget that there's got to be a cold joint. Concrete's poured in stages. The columns get poured up to the bottom of whatever's the floor system is. The beam, the slab, whatever it is. And that creates a cold joint. And we need to connect one piece of concrete to another piece of concrete. And that's what happens. You need to give it a place to either sit on or connect to. Anyway, that's just something that's come up recently. This, another thing I get in trouble for saying, this is the building next door. Anybody want to tell me what type of construction that is? It's not pre-stressed, it's not post-tension. Tilt up. How can you tell? Because they're tilting it up in the picture, yes. Now they'll pour these big panels laying down. Then they tilt them up using cranes and wires. Then they hold them in place and wait for a floor or roof system of some very light joists, metal deck to come and hopefully kind of brace it. And do they stay there forever? No, they just stay there till the next earthquake. I shouldn't joke around about that, but this building has suffered terribly in earthquakes, this type of construction. But that doesn't stop them from tweaking the numbers a little bit and coming right back and doing some more. It is the least expensive type of construction, but everybody's got their thing. I think there's nothing better than casting concrete in place, in forms, post-tensioning it, and that building is solid. To me, it's the most solid seismic diaphragm. It's the most solid seismic system. It is the most solid vertical system for resisting loads. A tremendous redundancy in cast-in-place systems, and particularly, one thing I forgot to mention, do you know what the limit is? And again, I don't expect you to know this answer, so just throw out guesses is fine. But how long can a piece of rebar be in a building? There's a practical limit.
40 feet.
60 feet. 40 feet, 60 feet. 60 feet. And that's all driven by highways. That's the maximum length something can be on a highway and be transported, unless it's got some special permits and all that. So you learn that you need to detail your jobs not to have steel longer than 60 feet, really because the steel can't get to the job site on a truck. So post-tensioning steel, you're going to see in a minute, can be 300 feet long. So what do you have to do with the mild steel if you want it to be longer? What do you do to it? Splice, lap. You lap it. You some distance, you run through all the code equations, and there's some 7 feet, 8 feet, 4 foot 6, 52 inches of lap in 4,000 psi concrete. If it's a Class B type, then all that stuff in there. But basically, they say that if you do that, you satisfy all these conditions, and you've got enough cover. You can effectively transfer the force from one bar to another. So you've effectively made it just a continuous bar, but you have to do that through a lap, and you have to be careful how you do that. In pre-stressing steel, you just unroll it. It is one piece of steel. We never have to think about laps in pre-stressed concrete. Another benefit. Okay, so that's what a cast-in-place post-tension concrete building will look like. This is a parking structure. This was the situation where I told you. Typically, you'd want to use columns to support beams, but if you've got a drive-through, you can't have a column right there. The parking consultant won't let you, so you put in a girder. We'll post-tension that girder too. Post-tension my grandmother if I could. This is the top of the same situation. Okay, this is an interesting one. This in my early career, this probably put me on the map. This is the one job where I can think of where I went from being a nobody to being a somebody. This is the Howard Hughes Center, and KPFF is actually designing all the steel buildings out there. We got 5 parking structures around there, and KPFF ended up moving into one of those. And if you go interview or you go over to their office, that's where they are right now, is at the Howard Hughes Center. What's interesting about this is this one's almost identical to what your project is going to be. You're going to have a 2-span system. I've actually given you a different live load on one side than the other side and changed the spans to make it more fun for you. But you're going to design a 2-span beam with columns. And that's a typical post-tension concrete parking structure. What's not typical about this is this level. We really didn't have any more headroom to work with, but we had to put an entire park on this. And if you go to the KPFF offices or any of the other businesses there, you know, they're out there having lunch and sitting around, and I would bet most people don't realize they're on a parking structure. They just think they're in a park sitting there. Now, most of this is foam. We've gotten really good at using what's called geofoam and using that for a lot of different things. That's only about 15 inches of soil, and we had some boxes for these trees in here. But none of that would be possible without pre-stressed concrete. This just could not be done in reinforced concrete and be this thin going this far. This is about 65 feet. Those are 3 foot deep. We doubled them up. That's the secret up at the top level. But tremendous load, live load's much higher, believe it or not. This is one of those funny things about the code. Assembly load in the code is about 100 pounds per square foot. Parking load, cars, SUVs, parked stall after stall after stall, what's that? Anybody know? 40. I have so much trouble explaining to owners that in a retail situation or a wide open space, we have to design for 100 pounds a square foot. And that's 2.5 times what we have to design for in the parking area, which has valet parking effectively for SUVs. It's one of those hard things to understand, but that's the truth of the matter. Car loading is the lightest loading that there is in the code. It's apartments is 40 pounds a square foot. There's nothing less than 40 that I'm aware of that's in there. And car loading is 40 pounds a square foot. It's right there at the bottom. It's about everything else is higher. Okay, this was many months later. I had been standing on the other side looking this way. Now the building's been built. I'm now standing here looking that way. This is that park, and I tell you, most people, no idea that they're actually on an elevated structure right there. This comes right off of our drawings. This is a typical beam elevation, 2-span. You are going to produce a drawing that looks just like this. You're going to tell me every piece of information that I'm showing here. You, on your project, will calculate how many pre-stressing tendons there need to be. Each one's a 1/2 inch, by the way. In reinforced concrete, you have a number 4 bar, number 5, number 6, number 7, and you change all kinds. We only have one for all practical purposes in pre-stressed concrete. It's always a 1/2 inch steel. Now, in bridge design, they have some larger ones, 0.6 inches, but for all building design, parking structure design, podium design, bank, medical office building, we're talking about 1/2 inch tendons. So, and they're always good for, we'll stress those to be about 26,000 pounds. So you're going to have to figure out how many of those you need. In this particular beam, it's 11 strands, but it'll be part of your design. We'll do it together, don't worry. We'll be determining the pre-stressing steel. Now, in any pre-stressed concrete member, post-tension concrete member or pre-tension, there's also always bonded reinforcement. There's also always the same reinforcement that you learned about and designed in reinforced concrete. You think of pre-stressed concrete, the pre-stressing steel is additive to that. It is the primary reinforcement, but it still will always have mild non-pre-stressed steel also in the beam or slab. My father's kind of going to go over the history. If you know, it's not mandatory that you go to the discussions, but the first one, he's going to talk about the history of pre-stressed concrete, and I've moved that to the discussion. I'd really like you to try to make that, because I will ask 1 or 2 questions on the final about that. And you know, if you absolutely can't make it, contact me and I'll give you some material or something. But basically, it's interesting. He does, you know, he was there. This isn't, you know, what he read about. This is what he lives. So it didn't make any sense for me to tell you the history of pre-stressed concrete when I've got a father who lived it and helped develop it. So he's going to tell you about it. But this is, you know, the early iteration of pre-stressed concrete. This is what's called a button-headed tendon. You know, they had to kind of figure out how it was going to work. They had the great idea. T.Y. Lin came up with it. Fresnay maybe came up with it in France, but T.Y. Lin made it popular in the United States. But they still didn't know how to physically do it. The idea was there, but how do we actually do it? And this was the first iteration that didn't work out so well. This is the next iteration that also didn't work out so well. They tried a spring coil and thought I'm not even 100% sure, but by getting all the concrete and grout in there that it would just lock it up, and they kind of trumpeted it down, but those things failed way too often. Then they came up with the right answer, and it's the same answer we've been using now for decades, and it works. This is the Sherlock anchor. This is 2 of them. I've put one side by side and just turned it over so you can see front and back. But at every tendon, at every single half-inch tendon, one of these will be placed. It has a kind of a trumpeted, tapered hole in it. The tendon will come out. The pre-stressing strand will come out. These wedges will end up going in, and as it tries to recoil back in, it, stress it under tremendous force, and then when it tries to recoil, those anchors, those wedges will lock it in. That works, and that's been successful, and nobody's trying to come up with anything different. We came to equilibrium. We found something that works, and that's what it is. Okay, I'm going to start moving along because I'm running late. But this is the DSI plant in Long Beach. It's actually just a big coil of half-inch pre-stressing steel. I told you it gets greased, so here is the ugly, messy greasing process. This is called a strand, and I'm going to use the word strand and tendon interchangeably because I'm lazy and I'm sloppy, and I have been. They're really the same thing. The strand is just the bare steel. Strand, just steel. Tendon is going to be the whole system of grease, plastic, anchor, and strand. So technically, ACI's definition of tendon is a strand with grease on it, with plastic around it, anchored at the end with an anchor. That's a tendon. That's one system. The strand is just the steel in it, but most of us are lazy and we just interchange the word strand and steel. This is where the hot molten plastic gets put on. It's loose around the tendon or the strand as it's coming in, and it goes right into this water trough, which cools it down immediately, and then it shrink wraps right to the grease and the strand. This is the high-tech counter that they had when I was there, and tells you'll specify off your jobs. They'll have to determine, it won't be you, but it'll be the person creating the shop drawings off of your drawings. We'll say that there's 40 124-foot long tendons, so they will cut 40 140-foot long tendons at that plant, and there'll be 30 160-foot long tendons, and shop drawings will be created, and this is how that will be made. They will show up at a job site in a big bundled roll. That's why I said there's no 60-foot limit. They'll just wrap these. They'll just roll these, and they can make them really as long as you need it to be. Back at the job site, they will really just unroll these. This is a construction joint. The reason we use a construction joint is because floors are often bigger than the concrete subcontractor can place at one time. They're usually in about the 20, 22, 24,000 square foot. And you can easily be on a job that has a 100,000 square foot floor. So they'll do it in sections. Again, another benefit of pre-stressed concrete is you can just unroll that, unroll it right through the form, and just leave it there waiting to be unrolled for the next pour. See if I can get this right. This is actually placing concrete. This is a flat plate job. This is mostly what I do. It's a little bit more of a specialty. There are no beams in this system. Everything is done within one flat plate. But that's the funny thing about this is they called me out for a structural observation. They're supposed to call me the day before they're pouring concrete so I can look at it and say, that's right, that's wrong, that's right, fix that, do that. No, they accidentally called me on the day, or scheduled me on the day that they're actually placing the concrete. So I just pulled out my iPhone and took a picture, but watch this. Who's this guy? He's the most important guy there. I want somebody to guess and tell me what they think he is doing. Vibrating the concrete. Always important in any concrete. You can hear him over here. In my opinion, in post-tension concrete, this guy is the most important guy because I'm about to show you pictures of what happens when the concrete is not vibrated correctly near the anchors. And at the anchors is where all this tremendous force is coming in. 26,000 pounds at every single anchor. And we'll line up 30 of them in a row on one of these flat plates. And, you know, bad things can happen. This is kind of an irrelevant slide now because the 2014 code mandates that all tendons be entirely encapsulated. That means they are isolated entirely from the concrete elements, water, salt, anything that can get in there. They're living inside. That steel is living inside and will never be in contact with anything. That keeps it from corroding. This is an encapsulated tendon on the site. This is a slab on grade. Actually, slabs on grade are the most popular. When I say most popular, more post-tensioning is sold in slabs on ground throughout the country than in elevated structures, which is kind of fascinating to me. But foundations are, you know, that's quite a niche to get into. This is the pocket former. I think I told you, this piece of plastic that will come out. This jack will be placed in there. A pocket former came out. It created a hole. That allows that nose piece to go in. This jack locks onto the anchor and stretches it. And I'm not talking about picking up slack. I'm not talking about a loose tendon that just gets straightened out. I'm talking about PL over AE, stretching steel. That piece of steel will be stretched 8 or 9 inches. And I mean stretched. And it takes a strong jack to stretch steel 8 or 9 inches. But that's how force gets into a system. Tail gets burned off. This is a finished slab on grade slide I threw in. This is an assisted living facility in Pasadena, but this was our flat plate system. Notice that there are no beams in here. Like I said, this is actually how I make my living. It's not what we're going to focus on. I'm going to teach you more of the fundamentals of beam and slab design. The next step after that would be to learn how to take all the beams out and make it work just as a slab. This is that same, standing in that same place, because this was the restaurant I always went to whenever I did a structural observation. And I always took the picture, but you can't tell if that's a wood. That was actually originally designed to be a steel building. It's an assisted living facility. If it was a residential building, it would have been done out of wood. But with older people in assisted living facilities, they can't be in a flammable wood building. So the choices were steel or concrete. We saved about $1 million on this by converting it from the steel building to the prestressed concrete building. This is a podium slab. I wanted to do a Disney area hotel, so I got one called the Candlewood Suites, and it changed its name to the Greenwood Suites or something like that. But these are what are called podium decks. They are thick decks with capital caps holding up, you know, usually 4 or 5 stories of another type of building, wood often. And this is a parking deck down below. But all of that concrete is pre-stressed. That's what I would get hired to do. We did from here down. Another engineer did from here up. Another, you know, there was a time there when these things were hugely popular. We're not doing a lot of them right now. You know, construction goes in phases, and what's popular changes, you know, year after year. But right now we're doing what are called wrap parking structures. But so this is the wood framing on top of the podium, and an architect covers it all up, and you don't even know what materials you're looking at anymore. We don't like to do this, but I show you that we can. We can curve tendons in these flat plates, and the thing to think about is that not only does this tendon want to straighten up vertically, it wants to straighten out laterally, and people can get in trouble by forgetting that part of it. We did this. I don't like doing it, but I did take pictures of it. I try very hard now not to do it. As I get older, I get more conservative, and we've had a few good blowouts doing these things, so we don't do it anymore. When you put a lot of pre-stressing in one location, it is very important, and the code requires that you confine it. This is why. They were moving along. Everybody was happy. They were stressing. This is probably 3,000 or better concrete. And bam, at one point, because this concrete was not vibrated well, that guy with the vibrator didn't spend his time at the anchors. He spent his time way out here where it didn't matter. And the contractor ignored our detail about confinement because this was a construction joint. They thought it only applied at the edge of the building. And we told them, concrete's not all that smart. It didn't know that this wasn't the edge of the building. It thought it was the edge of the building. So it exploded. You know, this is high-strength concrete, and it's nothing but dust. And, you know, people will tell you, I'm good at pre-stressed contractors. Well, I'm good at this. I know. I've done a lot, you know. Well, until they've had a real blowout, they don't really respect it. And these blowouts are good every once in a while. It unfortunately goes out and causes people who quit smoking 10 years ago to start smoking right then on the spot because there's concrete chunks this large, 40 feet away, that were flying by them. And they say, wow, I respect pre-stressed concrete much more than I did yesterday. There's going to be a concept that we're going to talk about, but overbalancing. You can drape too much. You can put too much post-tensioning in. And that is the biggest problem in pre-stressed concrete, is too much. And that's why engineers are scared of it. You can't really make a steel beam too large. You can't really make a wood beam too big. You know, nothing bad happens when you do more. And engineers, this is good, more's better. And that's what you're taught. That's what we're all taught, right up until you get to pre-stressed concrete. Too much can explode things. Too much can cause this big, huge bubble to shoot up on a building. The problem in this was not our building. This was an engineer who draped and designed putting all the loads on the building. There's a 4 or 5 story building coming, but it's not there when it got stressed. Totally forgot that one of the controlling analyses in a pre-stressed concrete building needs to be when there's no load. The no load situation can be the worst case. You know, you put 450 pounds a square foot on this, and that might not have happened. But you've got to understand that in pre-stressed concrete, you have to look at every possibility. You have to look at what happens when there isn't load there, and you can overdo it. So pre-stressed concrete is getting it right. It's not doing too much. It's not doing too little. It's figuring out exactly the right design. This is looking at that from another direction. Look at that. This is supposed to be flat. This was very expensive fix, by the way. Punching shear is a big problem in all of concrete, particularly in pre-stressed concrete. We will make the decks thinner, and if you do flat plates like I do, your biggest thing you're going to worry about and keep you up at night is this, that because you made that deck thin, that you don't want it to punch through. This was the Northridge earthquake. It punched through because it lost connection to the seismic system, but all it needed to do was move enough to create a shear beyond the capacity, and this thing came down. This is back in the building about 60 feet. This is hard to see, but that is the nub of a column. This section of the building didn't fail. The one end failed, but as you walked back into the building is actually not failing anymore. It's actually held up. And it's held up, this is hard to see, because a few post-tensioning tendons, those green things, actually got caught up on the top of the column, and that kept the entire deck from falling. Now, this is one of the dumbest things I ever did. I crawled in underneath and took this picture. I never would recommend doing that. I will never do it again the rest of my life. But these are the kinked post-tensioning tendons coming over. Just a couple of them in each direction were enough to hang up on this column. You know, that cap's gone. That's just, you know, rubble of concrete right now. The only thing that kept this building from collapsing, by the way, this is an apartment building with 4 levels, and just about everybody was home. And for the most part, there were no deaths. But had this not been a post-tension concrete building, probably the entire thing would have failed. So when we're doing this, we make sure to get a lot of pre-stressing steel, a lot of post-tensioning tendons right through the column. We use, not only do we do that, our steel goes right through the column, so in a terrible event, that steel would hang up on that column. We also reinforce with shear studs. I know I'm going too long, I apologize, but you got to understand that pre-stressed concrete, when you put that much force in it, the deck wants to move. This is probably a 250 long deck. We're at one end of it. This deck wants to go. When you squeeze it, it's squeezing and it's coming in from all sides. And if you don't let it come in, it will lock up on whatever it's trying to slide on and do something like this. This was another engineer. I told you we do what's low, they do what's high. Another wood engineer was supposed to design all this. He put a plate in. We told him, don't connect through our deck. We have a slip plane. We have masonite board there. This needs to slip on top of that concrete, that masonry wall. Well, he put dowels in, told us he didn't do it, and then we stressed and said, you want to tell me again that you didn't do that? Those dowels in there from that plate came down into this, grabbed onto that, and just tore that masonry wall apart. That's out in Palm Desert. This is external post-tensioning. I've talked about that. If you come down to Coronado, you'll see what it looks like. This is actually the Coronado apartments. This is what you're going to walk up to and look at. We did Coronado in a couple phases. We did the slabs first, and then we came back and we did the beams years later and put a new slab up on top. But this is what you will walk up and get to see and look at. This is looking right down a beam. That's the end anchorage plate, but it's all exposed. And I'm just going to flip through. This is an Embassy Suites in Palmdale. We do hotels. We did Embassy Suites in Ontario. They're fun. This was all, the front was all designed in steel and the back was designed in reinforced concrete. We made it all pre-stressed concrete, saved a boatload of money and had a lot of fun doing it. Embassy Suites oftentimes brings their pool inside the building, so we had to long span across it. We got a lot of different framing, which, you get to be my age, that's the fun you get to have. This is the gunite pool within the building. Those are the metal studs that give the building its final effect, and off of Expedia I went on, and you'll have fun someday. You'll be able to go on Expedia and go on the internet and take pictures of your own jobs, and that's a fun thing to do. So that's, if you look on Expedia and you want to stay at the Palmdale Embassy Suites, that's the picture that's there. Okay, sorry for running over. I will see you on Thursday.